So in this video, we're going to do a surveyor application of trigonometric functions. So a surveyor can measure the width of a river by setting up a transient at a point C. So we're starting at this point C here on one side of the river and taking a siding of point A on the other side of the river. And after turning through a 90-degree angle, we walk until we get to B. Okay, so we step off 200 meters. And then at B, we transist to the angle of measure that gets us back over to this point here. And it turns out that angle that gets us back over is 20 degrees. So we're going to use this information to figure out this distance x across the river, okay? So to do this, what do? We use trigonometry. What sides do I know? I know the opposite side and I know the adjacent. So some old hippie caught another hippie tripping on acid. That's tripping on acid. Okay, so how does that work? That's the tangent of 20 degrees is equal to opposite over adjacent, 200. And so if I multiply by 200 on both sides, okay, 200 times tangent of 20 degrees, 200 times tangent of 20 is 72.79. Okay, so 72.79 meters. Okay, rounded to the nearest meter, 73 meters rounded. All right, not too bad. Okay. Now this next problem, next application, finding the inclination of a mountain trail. All right, how does this work? So say we've got this, little hotel here. Got some windows, right? Look at that pretty, happy little hotel. Now the elevation at the hotel, elevation of 8,000 feet, okay? And so this trail works its way up. And so looks like a straight trail leads up the Alpine Hotel. Elevation is 8,000 feet to a scenic overlook at an elevation of 11,100 feet. So maybe this is a scenic overlook. Elevation 11,100 feet. All right, the length of the trail is 14,100 feet. So this length here of that trail is 14,100 feet. And we want to know what is the inclination, the grade of the trail. Okay, so that is what is the angle B right here. So this is a right angle here. So that's what we're trying to figure out. So here we're trying to figure out the angle and not the side. Okay. Well, do we know any other sides? We don't really know this side that kind of cuts into the earth, right? However, we do know this side here. Okay, this side here is equal to, well, it's the difference between the elevation at this level versus the elevation at the hotel level. And what is that? That's 11,100 minus 8,000 feet. So that's 3,100 feet. Okay, so this side's 3,100. So what do we know? What trig function does opposite over hypotenuse? That's sine the sine of angle B is equal to 3100 divided by 14,100. Okay. Now what? To get angle B, I take the sine inverse of both sides. So B is equal to the sine inverse of 3100 over 14,100. This is perfectly fine because what we have is a number that's between -1 and 1. So when I do this, I do the sine inverse of 3100 divided by 14,100, close parentheses, enter, I get 12.7. So this is roughly 12.7 degrees. Okay, 12.7 degrees. Now, vertical heights can sometimes be measured by angles of elevation or angles of depression. So how do we define this? So an angle of elevation, this is whenever we are standing and we're looking at an object and the angle is an upward angle. So the object is above. Okay, the object's above us. An angle of depression, okay, where do we look when we're depressed? We look down. So an angle of depression, when I'm looking, my object is below. So when I draw my triangle, my angle of depression is down. Okay, it's below. All right, so the horizontal line that I look at, if I'm above the horizontal line, that's an angle of elevation. If my horizontal line I'm looking at, I'm just below it, then it's an angle of depression. So this is your line of sight. And here's your line of sight. Okay. So when we work through an application here, if I want to find the height of a cloud, so finding the height of a cloud. Right. So meteorologists find the height of a cloud using an instrument called a ceilometer. Maybe I probably butchered that. A ceilometer consists of a light projector that directs the vertical light beam up to the cloud base and a light detector that scans the cloud to detect the light beam. Okay, so a little picture they've got going on here. Let's see, we got a little light stand. So it's shining a ray of light up to some clouds, okay? And then you've got another light stand, and this light is shining straight up. So this is the cloud height H, okay? And that base B. So this is the vertical light beam, and then you've got your light detector here, okay? So that's the ceilometer, okay? So a Midway airport in Chicago, a ceilometer was employed to find the height of a cloud cover. It was set up with a light detector 300 feet from the light projector. So you got your light detector 300 feet from the light projector, so 300 feet. Okay. From the light projector, if the angle of elevation from the light detector to the base of the cloud was 75 degrees, so angle of elevation equal to 75 degrees, we're going up, right? If we're in a cloud, we're obviously looking up, but Angle of elevation means it's above us. Okay, angle of depression is below us. Now, what is the height of the cloud over? So what is this height x? I use trig. Okay, so trigonometry says the tangent of 75 degrees equals what? It equals x over 300, opposite over adjacent. So x is equal to 300 times the tangent of 75 degrees. If I type that in my calculator, I'm going to get 1120 approximately. Okay, so 1120 feet. All right, so the ceiling was approximately that far, the height to the base of the cloud. Okay. Doing a couple more applications, finding the height of a statue on a building. So the height of a statue on a building. Okay. Adorning the top of the Board of Trade building in Chicago is a statue of Crease, the Roman goddess of wheat. So sure, I said that wrong, but whatever. From street level, 2 observations are taken 400 feet from the center of the building. So there's an angle of elevation. So we've got a building. Okay, and at the top of the building is some statue. Okay, and so 400 feet away, they take 200 two measurements. So 2 observations were taken at 400 feet from the center of the building. And so this distance right here, so that's right there, the center of the building for that statue. The angle of elevation at the base of the statue, okay, this angle of elevation was 55.1 degrees. And the angle of elevation to the top of the statue, not much more, but it's a little bit more. That angle, theta 2, I'll call it, that was 56.5 degrees. So now the question is, what's the height of that little goddess or whatever is on the top of that building, right? So how do we figure this out? Okay, so what we can do is we can use trigonometry, right? If all I'm looking for is this little piece here, okay, all I need to know are the sizes for the 2 triangles. So I've got 2 triangles. One of my triangles is 400 feet, and I have an angle of 55.1 degrees. And the other triangle is slightly bigger side here. So this is my x1 and this is my x2. It's slightly longer, x2 is than x1, and because its angle is slightly bigger at 56.5 degrees. Okay, so I have trigonometry. The tangent of 55.1 equals x1 over 400. And then the tangent of 56.5 over here is equal to x2 over 400. So if I multiply by 400 on both sides, so I multiply everything by 400, so this number here, when I multiply that out, I get 573.39. And when I multiply this out, I get 604.33. So the difference between the two is this distance. So that's 604.33 minus 573.39. So this is approximately 30.93 feet. So roughly 31-foot statue. Okay, so using 2 triangles, okay, and then I take the difference between those 2 opposite sides, and I will figure out what the height of that little statue is there. All right, one more, and I think that'll probably do it for this type of solving. And so with this problem here, this is the Gibbs Hill Lighthouse, Southampton, Bermuda. Okay. So in operation since 1846, the Gibbs Hill Lighthouse stands 117 feet high. Okay. On a hill 245 feet high. So its beam of light is 362 feet above sea level. So you got your little lighthouse here. Okay. It's 362 feet above sea level. Okay. A brochure states that the lighthouse can be seen on a horizontal about 26 miles distant. Okay. So 26-mile distant. Verify the accuracy of this statement. All right. So how do we know? So we're kind of talking about curvature of the earth here. Okay. So this lighthouse, after a certain amount of time, the earth is going to curve away, and then you're not going to be able to see the lighthouse anymore. Okay? So the question is, how do we know how far until we get where we can't see the lighthouse anymore? So we're kind of looking at that tangent point here. Okay, so what do I need to know? I actually need to know the radius of the earth. Okay, so the radius of the earth, oh my goodness, right? So the central angle, theta here, is positioned at the center of the earth. Okay, the radius of the earth is 3,960 miles. Okay, radius of earth. Okay, and then it's essentially the same thing here too. So 3,000 960 miles. Okay, but I also add this piece right here because it's a little bit further. So it's 362 over 5,280, because that's how many feet are in a mile. Okay. So how do I work this problem? Well, this is adjacent divided by hypotenuse. Okay. So the cosine of theta is equal to 3960 divided by 3960 plus 362 over 5,280. Okay, so this is the cosine of theta is roughly 0.999982687. Okay, Now, if I do the cosine inverse on both sides, 0.999982687, then I'm going to get roughly 0.33715 degrees. Okay? Yikes, right? So if you converted it, you could convert this to minutes. This is degrees. If you convert to minutes, it would be multiply 60 times this 0.33715, which gets you 20.23 minutes. Okay. So the brochure does not indicate whether the distance is measured in nautical miles or statute miles. So let's calculate both distances. Okay. So the distance S is the nautical mile. So this black curve, okay, that's the nautical mile. Okay. And this is given S equals R theta, right? So that arc length is S equals R theta, where theta is in radians. Yikes, right? So this in radians, theta equals 0.33715 times pi over 180, which rounds to 0.00588. Okay, so that's really small, times R. So times R, so S equals R theta. So R is 3960 times 0.00588, which is roughly 23.3 miles. All right. So 23.3 miles from there. So in either case, it would seem that the brochure overstated the distance somewhat. Okay, so somewhat overstated, even though, they said it would be 26, and it's not even 23. It's a little bit over 23. So looks like it's a little bit overstated. All right.